I was tasked to talk about the acceptance testing using the lightweight deflectometer or the falling weight deflectometer. So that's what we're going to do. And I'm not going to let you use your cell phones. You know, it took me 15 years to convince my children at dinner that put your cell phone down. And I have a bad reputation that when we are sitting in a meeting among students, you know, thou shalt not use your cell phone. So sorry, Richard, I'm not going to do that. But I'm going to ask questions. I have a reputation to keep. So, but he said that be lively and be entertaining. So the first question, what's funny about those two pictures I have over there on the right? Well, we use the Proctor hammer to represent the roller, right? So, wasn't very funny. Okay. Okay, no problem. Okay, let's start looking at the traditional density-based compaction. You know, we usually use the moisture density test, Proctor test, right, to come up with a basically moisture density curve, and so that we can judge what's the optimal moisture content and what's the highest density we can get. And then we go with a nuclear density gauge to verify that we are getting those two numbers, or one of them, at least density in Texas is prevalent. And then I have this picture at the bottom. I call it the lonely man in the field. You know, we usually go every several thousand square feet, and we just do one test, and we accept it, right? Okay, so let's see if we can change some of these things. One issue right at a time, you see that, you know, when we do the laboratory, we do tests at a certain energy. So we get one of these 5 curves that you see, or 4 curves, you know, I guess I'm seeing double. One of the 4 curves that you see. When the roller is compacting, they are not looking at the energy. They're just basically going back and forth till you get the density that you want. So any of those 5 points that I put over there on the red line is a valid answer. Now the question is, do they have the same modulus? This good-looking dude is Ralph Proctor, the person who came up with the moisture density test, right? Everybody, they call it Proctor test, you know. Oh, here's it. I would like to code a couple of things before we go any further. Number 1, strength is not achieved by density alone. And optimal moisture is for compaction. So we use optimal moisture content to compact, not anything else. These are from 1930s. Huh? And then these are not well documented, but this is 1945. He wrote a very pioneering paper relating to compaction. So the first one. This is related to a huge dams that they were building in California at the time. This is a prosperous time in California. It says no use is made of actual peak dry weight. Basically, they didn't use the maximum dry density for anything. Measure of soil compaction used is penetration resistance. So they use penetration resistance. Okay, now you wanted a question. This is the question. Anybody knows what this is? Or have you heard of it? The answer is Proctor penetrometer. Actually, Proctor not only came up with that mold and a hammer, he had a series of penetrometers that you buy, and basically the acceptance was pushing this into the ground. Somewhere around the World War II, we forgot about the penetrometer, and we started conveniently talk about density alone. So that was my grumpy old man side of it. So let's get to the technical side of it. So Proctor, the guy who came up with the idea of looking at the density, he tells you not to use density for acceptance. We forgot that. Okay, why modulus based? So that was one against. Now let's go to the, well, we want a long-lasting pavement. So in order to get that, we have to have a stool with 3 legs that are the same. One is construction quality, one is structure design, and the third one is the material selection. So we have to do all three of them well to get a well-performing pavement. We are hoping that these three legs of the stool are the same size, or it gets annoying, right? Let's assume that it is. But these three legs have to be attached to each other too. Okay, so let's see what we are doing. The connection between construction and structural design is broken. Simply, we do not check whether the modulus that the designer used is achieved. The structural and material leg is not attached either, because we don't check if the material selected provides the modulus that the designer intended to do. Construction quality and material selection is broken as well, because essentially when we are using moisture density device, we are just basically buying the material by the kilo. We don't care what the modulus is. We just basically, the denser the better, right? That's buying material by the kilo. So let's get to what Richard asked me to do. Talk about and Dave. Talk about the devices that we, basically the following deflectometer, or lightweight deflectometer. The following deflectometer, I'm sure everybody knows in the room. We have 16 of them in Texas. I guess now 6 or 7 of them. We have quite a few of them, and it's been used for the last 30 years. And the lightweight deflectometer is just on the side, as you see. I guess there was a, oh yeah, I found it. Okay, you see that? Basically, it's at the same plate as a polymer deflectometer. There is a weight that you can easily pick up and drop it on the pavement. So instead of being machine-driven, it's run by the muscle. Okay, I would focus on the lightweight deflectometer, and there's simply one reason. It's more practical. The concepts are the same. What is not practical? A polymer deflectometer is around $250,000. With that money, you can buy around 20 to 30 lightweight deflectometer. It's portable. You cannot have, if you have a dozen FWD, you cannot have it at every construction site. And more technically, you know, I don't want to get into the weeds. When you get a deflection basin on a soil or a subgrade or base, it's very, very difficult to analyze it, and it should be, because you're doing things that you are not supposed to do with the FWD. Okay. So the analysis is pretty straightforward. You know, you assume a Poisson's ratio, you measure or assume a load, and you measure the deflection. The machine gives you the deflection, and just put it in this equation, and you can get the modulus. And you run the test. I had a video, but Richard scared me, so I'm not going to do it because he wanted me to be on time. It's day to pick on Richard, right? Okay. Okay. Now, we go and run the test, and usually this is what we see that scares everybody. Oh, it's a random number generator. And that's the first time and the last time you look at it. No? So let's focus on that one. Why is there's variability in the modulus? So let's talk about it a little bit, huh? Maybe it should be. Okay, this is a very small experiment. We just got some clay, and we just basically prepared it at the optimal moisture content and maximum dry density. Tested it, got the modulus, and this is non-destructive testing we are doing. I'm not going to get to the detail, and let it dry with time. Okay, so I started at optimal moisture content and let it dry to 70% of the optimal moisture content. Huh? A few days. In El Paso, I guess it will be a day, huh? With 0 humidity and 100 degrees temperature, right? Okay. So you see that the modulus started at 26 KSI, and when you get to the 70% of the moisture is around 102. So it's a factor of 4. Now, we did a second specimen of the same material. Now we prepared it as 20% over optimum moisture content to the same density. So if you want your graduate students hate you, tell them that, just go trial and error. You have to figure out how much energy you have to put to get the same density as the maximum dry density. So the densities are the same between the two specimens. And now let it dry. So you see that it started now, when I prepared it, it was only 14, not 26, and it went all the way to 137. I have a wet clay, I put it, let it dry, it becomes a brick, right? So that's what it is. And the best one of all, if I do it at 80% of the optimal moisture content, the same density, I'm going to get, it's stable. Oh, okay. But now I have other problems that it's going to crack, so you have to. So if you see, it's kind of dark. You see that we are usually allow plus minus 2-3% moisture content, variability. So the area that you see between 96 and 14, anywhere you can get if you don't control the moisture. Now, all of this would give you the same density, because the dry density of all of them is the same, right? So if you are used to seeing no change in density and a change in the modulus, because we are changing the moisture. Moisture is important. So with that good news, let's now look at how the acceptance would work. This is coming out of a lot of work that we have done for TxDOT. Thank you. And a national project, an NCHRP project on developing a specification for the modulus-based acceptance. We just finished it a year ago or two ago. So the first step is selecting a suitable material. I'm going to talk about that. The second one is selecting appropriate design parameter, because that's what the designer uses. Right now they just basically assume, right? See if we can help them. Selecting target field value, field quality control, and then acceptance. These are the 5 steps that we have to go. Why I'm just putting the selecting most suitable material, have that in mind. Adequate stiffness, it doesn't mean adequate durability. You cannot separate that. We have a lot of experience how to, for instance, for the base, how the aggregate gradation should be, what's the hardness of the rock, what's the shape of the rock, things like that. We don't want to throw that. Those are all good information to have a durable material, not the material as you designed it. We design based on modulus, we are expected to get modulus. So we don't, just because we came up with a new gadget, we don't want to forget the 100 years of history that we have in road building. We have to combine both of them. Now, estimating appropriate design parameter. Okay, so there are different options that we have, and depending on the level of comfort, you can go with that. Okay. The best desirable one is conducting laboratory resilient modulus tests on the materials that you have selected. And that runs around $500, That's 1 minute of construction, less than that. But that's one option. The other one is just basically another pragmatic way. If just, especially for the bases and things like that, you know where the materials are, where the quarries are, you can just have a catalog of the numbers, right? So you can use that. There are some calibrated models. That's the second option, that if you know the PI, the gradation, and other index parameters, you can estimate what the modulus would be. And the least desirable one is usually a presumed value, like that the modulus of the base is always 30 KSI. It doesn't matter if it's El Paso or Orange. Well, that's the least option, the less desirable option. So I'm a geotechnical engineer, so I'd like to see a little bit of laboratory testing, because that's what we do for a $100,000 home. That $10,000 of it is the foundation. We do a test. Why cannot we do it for a few $1 million project? That's a question. So Now, this would be the feedback that will go to the designer, and we use the same number in the next step, which is selecting the target field modular. So if we know what the modular of the layer is during the design, okay, as part of the design program, we can easily just get the target value. And the target value, if you notice, I put it deflection, not modulus. Why? Because I don't want the technician to get an Excel sheet and start or a formula to put it. The machine measures deflection. Let's have the acceptance criteria based on deflection. There is no equations, there is no value and things like that. So we can do that. And if you want to look at it, the Minnesota Department of Transportation has a design program. I believe they call it MinPave. If you go over there, they have a tab over there. They immediately tells you what's the target values would be for each layer, on top of the subgrade, on top of the base, on top of the asphalt, what the target would be. Now let's get back to this pesky thing called the moisture. We have to be cognizant of the moisture. Okay. There are two moisture that we need. One is the moisture at the time of the compaction. The other one is the moisture at the time of the testing. So if I'm a good contractor, I will just finish the work on Monday, and I do the acceptance testing on Thursday. Guaranteed every time I'm gonna pass unless there is a rain, because it's drying, so the modulus is going up and up. The density is not changing. The modulus is going up and up. But at the same time, you know, we are in an era that we don't want to get in the way of the contractors. We want them to put the next layer as soon as you want. What these curves go over here is that the impact of the difference between the moisture at compaction and moisture at acceptance. So if we bring the acceptance very close to the construction, so we don't have to worry about it. That one would keep us happy because we do it fast, keeps the contractor happy because you're not getting in the way, you know, because you have to accept it before they can put the next layer. So the closer you bring this to, everybody would be happy. If you don't, I'm showing you the two ideal ones at the bottom. The top one is where the data is coming from. But you see that if you let the moisture content for a granular base, you know, a flex base, change by 2%, the modulus may change as much as 5%. This is very prevalent to us in Texas because we are the only state that we don't have a requirement for number 200 sieve. So we have a lot of fines in the material, more than any other state. If you're dealing with a typical subgrade, you see that, you know, if you let it dry by 4%, you're going to get a factor of 2 difference in the modules. But if you see it's within, at the beginning, they are very close to 1. So you have a window to do the testing, and then you don't have to worry about the moisture anymore. I would like to show you an experiment we did in LTRC. This is a lot of fun. Okay, so this is a LTRC, Louisiana Transportation Research Center. They have a accelerated loading facility, and they have a 250-foot area that they can build 10 different sections. So we partnered with them, and they get a 250 section, and you need for the roller to go back and forth. So we sacrificed some of that. So we have 180 feet in the middle. 12 feet is the lane. And I have the picture over there, and this I put it to prove to you this is a bona fide project. There are 5 guys with their hands in their pocket that they're not related to the project. That's for sure is a research project. And this is their ALF, you know, the accelerated loading facility over there that they can put it over there. So what did we do at this site? We just basically put five scenarios. We put the material dry, up optimum, at optimum, wet of optimum, and we saturated the material. And we asked them to pass density. And if you want to drive the contractor nuts, this is the way to do it. Okay. Okay. and this is, you see the red line is the optimum moisture content, and you see the lines. And we were asking for 95% minimum of the density, and you see that the dashed line is the 95%, and basically the saturated was, everybody knows when the soil is saturated, you cannot compact it, so we proved that, yay. But, but the rest of them, you see that they all pass the density quite well. Okay. So let's, I got carried away a little bit. So let's look at it. That the red line is the target that we were supposed to get. Okay. And then we see that the saturated one, there's no way. The wet one is getting close, but still we cannot get it. But the optimum we passed, and the dry we passed really well. So the moral of the story, if you are not worried about the material getting too brittle, just dry it, put it dry. You know. If you are worried about cracking, which we should go a little bit on the wet side. Okay. Now the other one I want to show you, we went from state to state. There are 5 different sites. I'm showing you different states, different projects. This is as part of the national. We just basically went, spent a couple of days with each of these places, and we collected data, or we just left them the equipment and say you collect the data. And I would like you to show all the sites. You see that they are passing the 95% maximum dry density pretty much at all the sites. This one doesn't have any density measurement. Do you know why? This is state of Indiana. State of Indiana has given away all their nuclear density gauge. State of Indiana, Indiana Department of Transportation, the whole almighty Department of Transportation has 3 nuclear density gauge left. They have 120 lightweight deflectometers now. So they are the first one that they plunged. Minnesota is coming, and Nebraska is almost there. So I guess maybe it's coming from Midwest, a little bit south. So we could not get density because they didn't have a nuclear density gauge to get density. And none of us knew how to do it the old-fashioned way, you know. So this shows the variability of the field condition of all the projects overall. And you see that, you know, we have around 20% coefficient variation. It's less on the bases and things like that because these are value-added materials. So we just expect it to be more uniform than the subgrade. One of the questions always come back is that, well, the soil is too variable to go modulus based. So I agree that soil is variable. So let's define the variability. You know, for us, 25% is uniform. But what do we do now? The soil doesn't change. The technology has changed. What do we do now? The soil is a variable right now as we go along, right? Just because we brought a new technology, the soil, the nature hasn't changed, right? What do we do now to manage that variability? Do we close our eyes, or do we go and test every, just because there is a new technology? I'm just asking, you know, maybe I should have added a question over there in that. But that boggles my mind. Okay, I agree with you, it's variable, but what do we do now to manage that variability? Okay, this is again, this is the global, all the projects that I show you, the variability of the, I'm sorry, this is one project, I'm just showing an example. We have the global in the report, you can look at it. And you can see that this is the variability. This is the cumulative distribution, like Steve was showing for the density meter. And you see that this is the moisture content and the allowance that the specification has for the moisture content. But you see that we are not much dry because dry is hard to compact, right? But we are significantly wet in some of the cases, right? Yeah, a little bit. This is another one. This is the maximum dry density. This is 95%. You see that around 50% of the time we are passing, 50% of the time we are failing. But we have only one data point, usually when we go to the field. So we don't. These are 40, 50 pages. We have students to keep busy. So when we go, we don't do one or two. We do 40, 50 at a time. I guess some of you, we have worked with you, you know. And this is the variability that you get from the modules. And one thing I would like to do, there is a target LWD. You see that I put an 80% of the target LWD. This is at this time to manage preliminary till we just get to to manage the variability in the soil. So where did that come from? That comes from just setting a precision and bias of the LWD. So, and you can look at it. And this shows a lot of different projects that I'll show you. This is you remember the moisture minus optimal moisture content. And this shows you that would be acceptance if you don't specify moisture content. It would be that. And then you see that most of these projects are passing, and whatever is below it is not passing the modules. Okay, now the question is how to handle the variability, right? Richard, I'm very, very scared. So one of the things that we hear a lot is a plate load test is the way to go. This is a gold standard. Let's say it's a gold standard. I'm not going to argue that one over here. Okay. What I'm showing you over here is a plate load test being run. And I think it takes 2 hours, 3 hours to run one, depending on the contractor. In that time, we ran 15 LWD around this one. So the middle, this plate is this one. So we laid that from plate load test 10 KSI. This is the contour map of the modulus. And this is 6 feet by 12 feet. I'm not talking about a huge area. So you can see the localized variation. Can you see the moisture over here? Can you see it over here? Okay. So you see that when this one is 10 KSI, it can be anywhere between 21 to 3. This is the maximum and minimum of the numbers over there. So is it really worth it to sit down over there for 3 hours to get one number, even if it's the gold standard, if the variability of the soil is there? So we would like to do a little bit more tests, and you get it. So how do they manage in these 12, the average of these 15 points? I show it with the average and a standard deviation, the error bar. You see that all the plate load tests except this one is just within the margin of that 25% that we call uniform for the subgrade. Okay. So maybe it's better to get that 3 hours. In that 3 hours, you can do around 150 to 100 LWD. Maybe it's worth it to put the energy in that one, huh? It costs the same. At least you have managed the variability and you have something to look at. There is one point that is off, but we have only 1 point, so it may be, this is not this point, but it can be something that they chose to go to a nicer, flatter, drier area while around it was wet. So this is what I'm suggesting. If you want to really read, just get more information, there is a Research Digest 391. We finished it 2 years ago. It's coming from the NCHRP, one of the NCHRP projects. Stephen Kasberg was just said intelligent compaction. We have a project for the acceptance along with the intelligent compactions, and we love to come and get a 500-foot section from you guys and see if we can do what Steve mentioned. I know we have some believers over here in those two technologies and some skeptical, so let's go and collect data so that we have data to show and make decisions based on data. With that, I'm done. Sure. I have 3 minutes for questions, so please speak fast. Okay. Steve?
I've got basically
Yes.
When do you test? And it's kind of on this theme of where your moisture is, but you obviously get a bonding, which makes it stiffer. The other question is, what if you got shallow depth of bedrock?
You could repeat his question into the mic.
Okay, sure. Steve asked two questions. First, what do you do with the cementitious material? That's a tough question. So you have not focused on that one yet. The reason is that what we have found, we have tested a lot. What we have found actually shortly after construction, when the cement stabilized material are softer, when they set, they're going to be the higher modulus. So we have focused so far on the maybe mildly lime stabilized, but not further than that. We have done the testing, but we would not have the answer yet to that one. The second question was shallow depth of bedrock. These are usually around the depth of the penetration is around 2 to 3 feet for these ones, so it's not like FWD. You don't see the bedrock usually. Unless you have shallower one, then why do you worry?
Well,
yeah. I know, but why do you worry? You should have a good performance material. Any other? Oh, yeah. Yeah, but you usually don't see it. Yes, sir.
You mentioned something about the compaction dryer material. You mentioned something about the cracking.
Mm-hmm.
When you compact dryer material, did you see on the surface cracking in that?
Yes, sure. The question is that I showed some data from when you compact material dry, right? Cracking is a concern. I mentioned that cracking is a concern. How are we have the evidence? There are a lot of evidence in the literature. We have seen the same. It's not as badly as for the high PI clays. It's not as badly when it's dry than you see it. But there is a lot of work in this area, and it becomes more ductile, so it's more brittle. It cracks. You may not see the evidence, but in terms of the. So that's why, like when they cover the waist sides with the clay liner, they usually put it on the wet so that it would not crack. But there's a lot of evidence that it takes a more effort to do it. It becomes stiffer. So if you think that you can maintain the moisture, you get a better, stiffer material.